Have you ever been there? You're running a critical deployment, pushing changes, everything looks good, and then just silence. Your whole CI/CD pipeline just grinds to a halt. Job's stuck, maybe pending, maybe waiting, and you're just staring at the console, wondering what on earth went wrong. We're going to zero in today on one of those really frustrating ones, parallel Jenkins jobs that deadlock when they try to deploy Helm charts. It's a tough one. So today's deep dive isn't about quick fixes. We want to really get into the architecture, understand why this happens. We've looked through the source material, the research, our notes, and the mission is to pull out the key insights so you can not only fix this when it happens, but ideally design your system so it doesn't happen in the first place.
Exactly. And, what we usually see isn't just one simple thing going wrong. It's often more like a perfect storm. Resource contention across multiple layers of the architecture. It's rarely just Jenkins or just Helm or just Kubernetes. It's the interaction between them. You've got Jenkins executors, Helm's own locking system, its mutexes, and then the Kubernetes cluster resources themselves. All three can contribute.
Okay, multi-layer lock contention. That sounds complex. Can you break that down a bit more? In this specific context, Jenkins, Helm, Kubernetes, what does that actually mean? Where do these bottlenecks pop up?
Well, fundamentally, it means you have these separate pools of finite resources at each layer, and concurrent jobs are all fighting for them. Think of Jenkins first.
Yeah.
It only has so many executors, right? Those are the worker slots that actually run the jobs. Limited supply. Then Helm comes along with its namespace level Mutex Locks. It's like a single lane bridge for deployments within a specific Kubernetes namespace. Only one Helm operation can modify or release there at any given time. That's its safety net. And underneath all that, Kubernetes has its own limits. CPU, memory on the nodes, maybe network IPs, shared storage like persistent volumes, multiple deployments hitting those at once. That's another potential bottleneck.
Right. So it's like a chain reaction. A block at one point can cause backups elsewhere. Okay, let's unpack this layer by layer then. Starting with maybe the most common one, Jenkins executors exhaustion. Sounds simple, but I bet it tricks people up.
Oh, absolutely. It's often the first place things go wrong, and maybe the easiest to grasp once you see the pattern. So picture this. Your Jenkins has, let's say, 4 executors configured, simple setup. Then maybe 4 developers merge code around the same time. 4 parallel parent pipeline jobs kick off simultaneously. Now, here's the catch. Each of those parent jobs needs to spawn a child job to do the actual Helm deployment. What happens instantly? All 4 executors get grabbed by the parent jobs. There's literally nothing left for any of the child Helm jobs to even start running on, and that's your classic circular dependency deadlock. The parents are sitting there waiting for their children to finish, but the children can't even begin because the parents are hogging all the resources, all the executors. It's a complete standstill. The fix. It sounds almost too simple sometimes, but it's about careful executor pool sizing. You basically need to ensure you always have at least one more executor available than the maximum number of parallel parent jobs you expect to run concurrently. That one extra slot is the key. It gives a child job a place to start, breaking the waiting cycle. It's not always about adding more compute. Sometimes it's just that small configuration tweak.
That makes perfect sense. A really common trap. I could see that. Okay, so assuming we've got our Jenkins executors sorted, enough breathing room there, what's the next potential layer of grief? Helm itself. How does its design contribute?
Right, Helm's internal mechanism. It uses those namespace level mutex locks we mentioned. It's actually a good thing usually. It prevents 2 different Helm upgrade commands, for example, from trampling all over the same release at the same time within one namespace, ensures consistency. But the problem comes if a job that holds that lock gets stuck. Maybe the Helm command fails halfway through, or it gets stuck in a pending install state because of some Kubernetes issue. If that happens, it might not release the mutex lock properly. And the big clue, the critical diagnostic indicator here, is seeing Helm releases stuck in that pending install state for a long time. You might also see leftover Kubernetes objects like orphan pods or services from a deployment that didn't fully complete or roll back cleanly. That usually signals the mutex was grabbed, but something went wrong and it wasn't let go. So that whole namespace is effectively locked for any further Helm operations until you manually intervene.
Ah, okay. So even if Jenkins is fine, a stuck Helm process can block everything else in that namespace. And then there's the bottom layer, Kubernetes itself. If Jenkins is okay and Helm releases its lock okay, how can the cluster still cause these deadlocks?
Yeah, Kubernetes itself has plenty of ways to become a bottleneck, especially with parallel deployments. You can run out of basic node resources, not enough CPU or memory left on any node to schedule the new pods your Helm chart is trying to create. That's a common one. Then there are things like network policies or ingress controllers. If multiple deployments are trying to update the same ingress resource or fiddle with network rules simultaneously, you can get conflicts or temporary failures. Shared persistent volume claims are another area. If multiple pods from different parallel deployments are trying to claim the same persistent volume, only one's going to win. And even things like service account tokens or RDAC permissions. If the Kubernetes API server is overloaded, or if there are issues with granting permissions quickly enough for multiple simultaneous requests, that can cause deployment steps to hang or fail, contributing to the overall deadlock.
Okay, this multi-layer picture is becoming much clearer. But theory is one thing. When you're actually facing this, pipeline's frozen, pressure's on. Here's where it gets really interesting. How do you diagnose this live in a running Jenkins instance? What tools do we use? You mentioned jstack earlier.
jstack, yes. That's really your go-to tool for diagnosing thread-level issues in Java applications like Jenkins. The standard Oracle recommended way to use it for deadlocks is not just to take one snapshot, but several, with a pause in between. So the typical approach is, say, 3 thread dumps, maybe 10 seconds apart. You'd run a command like jstack piping to a file, then sleep 10, then jstack again to a new file, sleep 10, and one more time. Why multiple dumps? It's for temporal comparison. You compare the stack traces across the dumps. If you see the exact same threads stuck in the exact same waiting state across all 3 dumps, especially if they seem to be waiting on locks held by each other, that's a very strong sign of a true deadlock. They aren't making progress. If the threads are changing state or moving between dumps, it might just be heavy load or contention, not necessarily a hard lock. You're looking for specific critical deadlock signatures. JStack might even explicitly report Java-level deadlock detected and show you the threads involved. You'd also look for Helm-specific patterns, like threads stuck in helm.upgrade.mutex.acquire trying to get a re-imprint lock. That points right at the Helm mutex. And sometimes you see Kubernetes client deadlocks, maybe involving HTTP3 connections stuck in network calls like socket red 0 or connect socket. That suggests the problem might be in communication with the Kubernetes API. It's detective work, really.
Okay, fantastic. That jstack technique sounds powerful. So we've done the detective work, found the specific lock or bottleneck. Now what? How do we fix it right now? And then, crucially, how do we stop it coming back?
Right. Immediate relief versus long-term prevention. For immediate resolution, once your JStack analysis points to the culprit, the specific thread or process holding the lock. Often, the fastest way to unblock everything is to, well, force kill that stuck process. It feels drastic, but if it's holding a critical lock like the Helm mutex, removing it might be necessary. You just have to be sure you've identified the right process. After that, you'll likely need to do some Helm release cleanup. Use commands like Helm list all namespaces pending or failed to find those stuck releases. Sometimes a Helm rollback might work on a failed release. But for truly corrupted ones, especially those holding mutexes via secrets, you might need to manually delete the relevant Kubernetes secret that represents the Helm release state to clear it.
Okay, kill the process, clean up the Helm state. Got it for the immediate fix. What about preventing this mess in the first place, architecturally?
Yes, prevention is key. A solid Jenkins pipeline architecture makes a huge difference. Using things like agent none at the top level of your Jenkins file means the main orchestrating pipeline job doesn't consume a valuable executor slot itself. Then you use declarative stages that specify specific agents or pools just for the deployment steps. And crucially, Jenkins pipelines offer named locks. You can define a lock, say lock Helm deploy production app. Only one pipeline execution can hold that lock at a time, effectively serializing deployments to that specific environment or application, even if multiple jobs trigger concurrently. Proper namespace isolation, designing your pipeline so each major application or environment uses distinct Kubernetes namespaces, completely sidesteps the Helm mutex conflict problem between different apps. And having dedicated agent pools just for deployment tasks prevents those heavy jobs from starving other, maybe smaller, Jenkins tasks. Beyond the pipeline code itself, there's advanced concurrency control. Jenkins plugins like the throttle plugin are really useful here. You can set limits on how many builds of a certain type or category can run concurrently. You can restrict builds per node or even set up throttling that understands parent-child job relationships. And you can build basic Helm deployment queuing into your script logic. Before running Helm upgrade, check if a release in that namespace is already in pending install using Helm status. If it is, maybe the script just waits or exits gracefully rather than piling on and potentially deadlocking.
That makes a lot of sense, building the controls right into the pipeline in Jenkins config. So we have immediate fixes, pipeline strategies. What about monitoring this proactively? At a larger scale, how do we spot trouble before the deadlock hits?
Great question. Proactive deadlock detection is all about monitoring the right metrics. In Jenkins, you absolutely want to watch executor utilization trends. Are you constantly running near maximum capacity? That's a warning sign. Track the job queue length and average wait times. If that queue starts growing and staying long, something's potentially getting bottlenecked. Monitor failed deployment rates, especially if you can break it down by namespace or environment. A sudden spike in failures for one area could indicate contention. And setting up alerts for thread pool exhaustion within Jenkins JMX metrics is also a good idea. Then, for Helm-specific observability, you need visibility into release states across all your namespaces. Tools or scripts that regularly check Helm list all namespaces and flag anything stuck in pending or failed for too long. Tracking deployment duration trends is also key. If deployments to a certain namespace suddenly start taking much longer, that could be a sign of increasing contention or locking delays. If you can, instrumenting your Helm calls to measure Mutex lock hold times gives you direct insight. And in automating the cleanup of orphaned resources, those leftover bits from failed Helm installs can prevent them from causing future lock issues.
And looking even further ahead, are there architectural shifts we can make to fundamentally avoid these kinds of problems, to evolve past them?
Definitely. That's where architectural evolution patterns come in. A big one is embracing a GitOps migration strategy. Moving away from Jenkins, pushing changes with Helm upgrade to a pull-based model with tools like Argo CD or Flux fundamentally changes the concurrency model. The GitOps controller pulls the desired state from Git and reconciles it within the cluster. This often happens in a more controlled, serialized way per application, reducing the chances of those simultaneous push conflicts that lead to deadlocks. Reinforcing namespace isolation, architecturally making it a strict rule that different teams or apps get their own namespaces is also huge. It eliminates Helm Mutex contention between unrelated deployments. And considering external deployment orchestrators like Tekton or Argo workflows, these are Kubernetes native tools designed specifically for complex workflows. They understand Kubernetes resources better and can manage dependencies and sequencing more intelligently than a traditional Jenkins pipeline might, making them inherently less prone to these kinds of deadlocks.
Okay, let's try to tie this all together. Can you walk us through a concrete example, maybe a common scenario you've seen in production? Let's say using CircleCI, but it could be any CI/CD tool, right? How will this deadlock play out, and how would we apply this thinking?
Sure, a classic case study. CI/CD pipeline plus Helm deadlock pattern goes something like this. Imagine two developers merge pull requests to the main branch almost simultaneously. Your CI/CD system, let's say CircleCI here, dutifully triggers two parallel pipeline runs. Both runs eventually get to the stage where they execute Helm upgrade for the same application in the same target namespace, like staging. Job 1 starts first, grabs the Helm mutex for the staging namespace, and begins applying changes. Job 2 starts milliseconds later, tries to run Helm upgrade for staging, hits the mutex lock held by Job 1, and correctly blocks, waiting its turn. So far, so good, technically. But then, Job 1 hits an error. Maybe a pod fails to schedule due to resource limits, or there's a brief network blip talking to the Kubernetes API. The Helm command in Job 1 errors out. Now, here's the crucial failure mode. Because of how the error occurred or how the job terminates, Job 1 fails to release the Helm mutex, the result. Job 1 is finished, marked as failed, but the mutex for staging is still locked.
Job 2 is still sitting there, patiently waiting for a lock that will never be released because the process that held it is gone but didn't clean up properly. Deadlock. The resolution methodology here. First, you'd spot the stuck Job 2. Then you'd investigate the namespace. Helm list -n staging might show the release from Job 1 stuck in pending upgrade or failed, even though the job is done. You'd use Helm list all namespaces pending or failed more broadly to confirm. The fix often involves manually cleaning up that stuck Helm release state, usually by deleting the corresponding secret in Kubernetes, like kubek tool delete secret-n staging, honor Helm status pending upgrade, or whatever the status is. It's also important to understand that the mutex should be tied to the Helm process, so ensuring the failed CI/CD job process, Job 1 in this case, is truly terminated is step 1. If that process hangs around zombie-like, it might still hold the lock conceptually. Killing the process, then cleaning the Helm secret state, usually resolves it.
Wow. That really illustrates how a seemingly small failure in one job can completely freeze unrelated jobs due to these hidden dependencies like the Helm mutex. It brings home that these parallel Jenkins job deadlocks aren't just, simple bugs. They really are distributed systems problems. Coordination failures across Jenkins, Helm, and Kubernetes?
Exactly. And understanding that multi-layer interaction is what shifts these from being mysterious, frustrating production fires to being diagnosable patterns. Patterns you can troubleshoot systematically and, more importantly, architecturally prevent.
It definitely makes you think. What other hidden dependencies or potential multi-layer conflicts might be lurking in our own CI/CD pipelines or distributed systems? That's a good thought for our listeners to take away. Thinking about that interaction between layers is key, especially when things get complex. And it's certainly the kind of deeper understanding that separates senior engineers, the kind of thinking that might even surface in a challenging DevOps or cloud interview scenario.
Precisely. It's about seeing the whole system, not just the individual components. That's all for this topic. Stay tuned for the next DevOps Cloud interview question.